Hi everyone, welcome back to Chapter 7. Let's get right into it. We're currently on Chapter 7.1, estimating a population proportion. This is part 2 of 7.1. So let's pick back up where we left off. So here we're going to construct a confidence interval using those steps and using what we went over in 7.1, part 1. So previously we noted that a certain poll of 1,487 adults, so a sample of the whole population of adults, showed that 43% of respondents have a Facebook page. So from this information in the question, we know our sample size is n is equal to 1,487. This is also going back to part 1 on how we defined a measure of success here and saying that an adult does have a Facebook page. Therefore, this p hat value is 43%, but put into a probability that's in a non-percentage form. So 43% divided by 100 is 0.43. We did initially cover this in chapter 7.1, part 1. So if you want to go back and see the full question, you can do so. So let's keep going here. Now we're asked to find the margin of error that corresponds to a 95% confidence level. We'll also find the 95% confidence interval estimate of the population proportion, or lowercase p. Then we'll go through this style of a question. So based on these results, can we safely conclude that fewer than 50% of adults have Facebook pages? For some context, we might have to write about a result like this, so we can assume that we are newspaper reporters writing a brief statement that accurately describes the results and includes all the relevant information. So step number 1 in working with confidence intervals, this also goes back to part 1. We need to verify that all of those requirements are satisfied. One of those requirements is that the polling methods used result in samples that can be considered simple random samples. We wouldn't want to go to the Facebook headquarters, for example, and poll 1,400 and so adults from Facebook headquarters, right? That would be considered a biased, non-random sample. The next requirement is, do we satisfy the conditions for a binomial experiment or a binomial distribution? So let's talk through each one of these. The first part, deciding are we satisfying a binomial distribution, is we have to have a fixed number of trials or a fixed number of samples. And here we do. We have 1,487 adults. We're not sampling any more in addition to that. So we're not sampling any others and then trying to add that data in after the fact. So we have this fixed number of trials. Also, the trials are independent. Here, the context of independent means that we can get a response from one adult, and the response from that adult doesn't affect the response from the other adult. The next part of satisfying a binomial distribution is there are 2 categories, either a success or a fail. And we have talked through this where we're describing a success is that an adult does have a Facebook page. And then the other category would be a fail, that the adult does not have a Facebook page. The fourth requirement here is that the probability remains constant. In other words, the probability of success or an adult does have a Facebook page is fixed for a given point of time. So for example, we wouldn't have a probability of 0.43 for one adult, and then some other time later, we have a different probability value. So probability remains constant. Okay, so we've checked off this requirement. We've kind of lumped all of this into just one requirement. Then the next is to say that we have at least 5 successes and at least 5 failures. So we don't know that directly from the question, so we kind of have to think through this one. We do know the total number of samples or the total number of adults that were surveyed. We were also given in the question that 43% of those respondents do have a Facebook page. So if we wanted to find 43% of our total number of samples, then we would take 0.43 times 1,487, we should get 639. So 639 is the number of successes. That's definitely greater than 5. Then if we know this percentage, then the other percentage, because there are only 2 categories, must be the adults that don't have a Facebook page. So we can either take 100% minus 43%, we get 57%. We could take 57% of this total number of adults, or 0.57 times this number. Or we can just know that there are this many adults total. So if this many adults do have a Facebook page, then 1,487 minus 639 is equivalent to 848. So our measure of success, an adult does have a Facebook page, there's 639, that's greater than 5. Our measure of failure is 848, adults do not have a Facebook page, so that measure of failure is also greater than 5. So now we've checked off all of these requirements, so this requirement check is done. If you have a homework question, for example, where we don't satisfy that we have at least 5 successes or 5 failures, for example, then we couldn't conduct a confidence interval in this way. So it is important to check off all these requirements, and because we have checked them, we can move on to the next step. Okay, so step number 2, use technologies, use Excel or Table A2 to find the critical value, or Z subscript alpha over 2, that corresponds to our confidence level of interest. Now, I like to use Excel, so this is how I set it up. I know my total number of samples, or my total number of adults, N is equal to 1,487. I also know my measure of success, or p hat, the sample proportion value is equal to 43%. Taking that out of a percentage, I get 0.43. Now, here below this row is where we get set up to solve part 2. So I know my confidence level of interest is 95%. We have done this previously, but I wanted to show you explicitly how I would set this up in Excel. So the next part of this is taking 1 minus this confidence level of interest, so 1 minus 0.95. We know that 1 minus 0.95 is equivalent to our alpha value. So our alpha value is 0.05. Next, we take alpha divided by 2 because we're trying to find this critical value here. So 0.05 divided by 2 is 0.025. I'm also able to do each of these calculations in Excel, so that's a nice touch. I don't have to worry about calculator errors and things like that. Then I would picture my normal distribution curve, and I want to find the z-score that corresponds with the cumulative area from the left. When I found alpha over 2, that's the area, that's the sliver of area that's on the far right-hand side. So I want to take 1, the total area under the curve, minus 0.025, so I get 0.975. In order to find that corresponding z-score that separates the large portion under the curve from that 0.025 area that's on this hand side of the curve, then I need to know an area value, and I need to know a mean, and I need to know a standard deviation value. We know that we can link a probability and an area value. So when we have this cumulative area from the left, that's our probability and our area value at the same time. We haven't used this normal inverse function in a little bit, so in order to use this, we need our probability slash area value, the mean, and the standard deviation value. We know the mean and we know the standard deviation value because we're dealing with a standard normal distribution here. So for cases like that, we know the mean is 0, we know the standard deviation is exactly equal to 1. So to set up this normal inverse function, I start typing in equals sign, norm dot inv, open parentheses, then my probability slash area value is 0.975, my mean value is 0, my standard deviation value is 1. I click enter, and I get an answer that way. When I click enter from this normal inverse function, I get 1.96. So this confirms what we got previously in part 1. What this 1.96 value is, that's our critical value, and in the same respect, that's our z subscript alpha over 2. Both of these are the critical value. This is the notation we use for a critical value. Let's start solving the different questions now we were asked in this example. So starting with part A, we need to evaluate the margin of error. So we've seen this equation before. Now we're going to practice using it again. So error, margin of error, capital E, is equal to this critical value, or z subscript alpha over 2 that we just figured out, multiplied by the square root of p hat, q hat, all divided by n. So what we just did on the last slide was figure out this critical value here. Now we also need to assign values for p hat, q hat, and n. We have talked about what p hat is in this scenario. We have also talked about what n is in this scenario. So we need to actually confirm what all these are, then plug them all into our equation. So from the last slide, we know that z subscript alpha over 2 is equal to 1.96. We have also talked about our p-hat value before. That's 0.43, or 43% of adults do have a Facebook page. Remember that we got that p-hat value, and we're calling that p-hat value our point estimate because we took a sample from a population and we're connecting that sample to be able to make inferences about our full population. We also know our number of adults here is 1,487. Then the only unknown left is finding q-hat. Going back to our binomial distribution discussion, we know that q-hat and p-hat are complements of each other. So the number of successes and failures has to equal up to 1. So let me show you how I put this into Excel. So far I have n is equal to 1,487. P-hat is the same up here. It's our sample proportion value. It's 0.43. To find q-hat then, because p-hat and q-hat have to add up to 1, then in order to find q-hat, we take 1 minus p-hat. So 1 minus 0.43 is equivalent to 0.57. So now I have all my information I need to solve for E, the margin of error. Because I want to use Excel for my calculation, I also put in this 1.96 here just to have all of my numbers right next to one another. So when I start solving for the margin of error, or E, then I can just have all my numbers visible. Then I start to calculate this. I know that E, the margin of error, is equal to Z subscript alpha over 2. So that's why I'm first putting this into the equation, where H8 refers to this cell, which is our critical value. Then I multiply that by the square root of p-hat, or 0.43, times q-hat, or 0.57, all divided by my same number of trials we've been using, or 1,487. I do want to show you in Excel that there's a parentheses here to designate what I'm taking the square root of. And then just to be extra sure that Excel is going to calculate this in the right order of operations, then I have an open parentheses here on this side of p-hat and on this side of q-hat. So I wanted to multiply these first, then divide by n. I'm taking the square root of all of this, then multiplying that by my critical value, or 1.96. You can definitely do this on a calculator too, but I wanted to show you how you can set this up using Excel. I think it's a nice way to do it. But if you put all these values into your equation, we should get 0.0251636. So there we just solved for the margin of error value. We have not yet rounded this off, but here's our margin of error, our E. So for our E value, we can actually keep this as the longer version of the number, and we'll worry about rounding off later. So let's keep going now to solve for question B. So in part B, we're asked to use the calculated margin of error, or E, and the value of the sample proportion, or p-hat, to actually find the values that make up our confidence interval limits. Going back again to part 1 of 7.1, we know that our confidence interval limits are going to follow p-hat minus E and p-hat plus E. So because we have p-hat and we just calculated E, we can actually solve for this already. So to remind you, here's our p-hat value, here's our E value. I'm going to show you how I do this in Excel. So here's my margin of error E value that we just calculated on the last slide. I also have my p-hat value listed here of 0.43. So we want to take p-hat plus E and p-hat minus E, so we can do so in Excel. If you prefer to use a calculator, we can take p-hat minus this value, and that's making up this side of the relationship. Then P, our population proportion, is in the middle. Then p-hat plus E is 0.43 plus the margin of error. Again, notice that we haven't rounded off yet. That happens now in step 5, so we need to round the resulting confidence interval limits to 3 significant figures. So again, here's our setup, and when we round this off to 3 sig figs, we have 0.405, then our population proportion here in the middle, and then 0.455. Something you've seen in your Excel assignments now is being able to use this here to then round off your values in Excel. So before I clicked here in Excel to decrease the number of decimal places, I had my p-hat plus E and my p hat minus E in their non-rounded forms. Then I selected those cells, I clicked here to then decrease this to just 3 significant figures. So this is our representation of the confidence interval here, so what I'm highlighting now. Let's try to answer part C now. So we know that this is our confidence interval. Here's our limit on the left-hand side. Here's our other limit. Then again, to remind you of this question, can we safely conclude that fewer than 50% of adults have Facebook pages? In order to solve this, we need to use this confidence interval that we just figured out. Now, before we get to the answer, I'd like to draw this out and show this pictorially. Our answer is where I've highlighted in the green box. We have our distribution. We figured out the 95% confidence interval goes from 0.405 to 0.455. So another way to picture this is we have our population proportion in the middle. Then we use a sample proportion to then figure out this confidence interval here. We figured out that p hat minus our margin of error is 0.405 and p hat plus our margin of error is 0.455. Then going back to our question, it does appear that fewer than 50% of adults have a Facebook page because the interval of values from 0.405 to 0.455 do not include 0.5, where 0.5 is equivalent to 50%. We're saying that the population value falls between 0.405 and 0.455. It does not contain 0.5 as a value here. Okay, so I really recommend drawing a diagram like this first in order to answer questions like this. Let's summarize all of our results here from this example. So 43% of adults have Facebook pages. We got this percentage from a trusted poll of 1,487 randomly selected adults. Remember that this is just a sample of our population of adults. Then what we also figured out is that in theory, in 95% of such polls, the percentage should differ by no more than 2.5 percentage points in either direction from the percentage that would be found by interviewing all adults. Now, where did this 2.5 percentage points come from? Because we had a 95% confidence interval, then taking the full amount of percentage points possible, or 100%, minus 95, that equals 5%. Then taking 5% divided by 2, that's 2.5%. What we're doing then is taking this 100% minus our confidence interval of 95%. Then we know that on either side of the middle of the distribution, we'll have the same percentage because this is all symmetric. Then the remaining percentage is 5%. Divide that by 2, we get 2.5% here and 2.5% here. The next topic in 7.1 is talking about analyzing polls. So when analyzing results from polls, we need to consider the following. I did not purposefully try to make that into a Bill Nye reference, by the way. So number 1, the sample should be a simple random sample, not an inappropriate sample or a biased sample. Next, the confidence level should be provided. For example, is it a 90% confidence level? Is it 95%? Is it 99%? It's also important that the sample size is provided. Number 4, except for relatively rare cases, the quality of the poll results depends on the sampling method and the size of the sample, but the size of the population is usually not a factor. It doesn't really matter that we have a certain million number of adults who are of age to vote. That number of total adults in the population doesn't really matter. What does matter is how we poll all those people, what's our sampling method, and how much of our full population shows up to be part of the poll. The number of adults that show up from the population in order to place their vote or be part of a poll, that's our sample size. The sample size matters and the sampling method matters. More on analyzing polls, so we need to be cautious and never think that poll results are unreliable if the sample size is a small percentage of the population size. If the sampling method is sound and samples are taken completely randomly, then sure, it can be representative of the population. And it can truly be a reliable way of getting information about a population, even with a small sample size. We can't necessarily rule that out. Additionally, what's been touched on as well, so the population size is usually not a factor in determining the reliability of a poll. The reliability of an election doesn't have anything to do with the total number of people that live in the US, for example. So next here in 7.1, part 2, we're going to go through how to solve different styles of questions. What I mean by that is we can actually solve for a point estimate of P, the value of the full population, remembering that point estimate of a sample is denoted as P hat. So we can actually solve for P hat if we know the upper confidence interval limit and the lower confidence interval limit. So we add those two and divide it by 2. Essentially, we're taking the mean of the upper confidence interval limit and the lower confidence interval limit. Another kind of question we can solve is for the margin of error. So to solve for margin of error, or uppercase E, we can also do something similar. So we can take the upper confidence interval limit minus the lower confidence interval limit and divide that by 2. In this style of questions, you may be given an upper confidence interval limit and a lower confidence interval limit, and then asked to solve for P hat, or the point estimate, or asked to solve for margin of error, or E. Okay, so you need to think about what's being given in the question in order to know, are we going to use a previous formula or are we going to use one of these formulas? Let's do an example now, finding the sample proportion and solving for the margin of error. For a question like this, for example, we're taking some information from a reputable journal. In the journal, we have this statement: of the 71 subjects, 70% were abstinent from smoking at 8 weeks. After this sentence, we're told a little bit about the statistics here. So 95% confidence interval, or CI, 58% to 81%. Now here's slightly different in how we approach this, because we're given 71 subjects, so that's our N value. We're also told 70% were abstinent from smoking at 8 weeks. In addition to knowing that we're working with a 95% confidence interval, we're also told in the statement that we go from 58% to 81%. We're going to use the information here to then solve for the point estimate, or P hat, and the margin of error, or E. The first important thing to do here is to figure out what this 58% to 81% actually means for us in the question. So for our solution, we get a 95% confidence interval of 0.58, so 58%, is less than P, which is less than 0.81. So what this percentage range is giving us, of 58% to 81%, that's giving us this side of this relationship and this side of this relationship. So notice that we haven't done anything with 95% confidence here. We're taking this percentage divided by 100 to get 0.58, and this percentage divided by 100 to get 0.81. We're taking these percentages because this is the lower end of our confidence interval limit, and this is the upper end of our confidence interval limit. So how we represent that is saying 0.58 is less than P, our population proportion, which is then less than 0.81. This setup here is one of the most important parts of answering questions like this. So recognizing, what do we do with these percentages? What do they mean? Then we can use the formulas we just covered in the last 1 or 2 slides to find the point estimate, or P hat. To solve for P hat, the point estimate, it's midway, or the mean, between the upper and the lower confidence interval limits. To remind you on that formula, we take P hat to be equal to the upper confidence interval limit plus the lower confidence interval limit, all divided by 2. So to set this up, the upper confidence interval limit in a non-percentage, very importantly, we don't use percentages here, that's 0.81. The lower confidence interval limit is 0.58. So we take 0.81 plus 0.58, divide that by 2, 0.695, that's our P hat value. Notice again that everything we've done so far only uses 58% to 81%. We haven't used any other part of the question. Let's continue on now and solve for the margin of error. So we saw that formula as well. We're going to solve for the margin of error, or E, by going from the upper confidence interval limit minus the lower confidence interval limit, all divided by 2. So here the upper confidence interval limit is 0.81. The lower confidence interval limit is 0.58. So we take 0.81 minus 0.58 divided by 2. That's 0.115. That's our margin of error value. So again, it's important to note that we just take this percentage range in this question. The 71 subjects we didn't use, the 70% we didn't use, and we didn't even use its 95% confidence interval. Okay, so pay attention to what we're given and just focus on the important data here. So we use 58% to 81% to solve for the point estimate, or p hat, and the margin of error value, or E. So as you saw, solving for p hat and solving for our margin of error were relatively straightforward formulas. We need to know the upper confidence interval limit and the lower confidence interval limit, and then know which is the right equation to use. Next, we're going to go into this example where we're finding the sample size required to estimate a population proportion. So if you're asked on a homework problem or in an exam, find the sample size required to estimate a population proportion. This is how we're going to do it. So first, let's talk about the objective. The objective is what you think it would be. So the objective, of course, is to find the sample size required to estimate a population proportion. The notation here is the same we've been using. So we have our p-value, our p-hat value, n, e, and z subscript alpha over 2. Next, let's talk about the requirements for doing this. So the sample size must be a simple random sample of independent sample units. These are pretty standard requirements here. We want to definitely take our data in a random fashion. We don't want to be biased. We also want independent sample units such that one sample unit does not impact another sample unit. Now, there's two different formulas we can use here. So when finding the sample size required to estimate a population proportion, we need to consider, do we know an estimate of p hat? Or do we not know an estimate of p hat? So if an estimate of p hat is known, then that'll of course go right here where p hat is. Then if p hat is known, we can also then solve for q hat by taking 1 minus p hat. Then this value here, that's our critical value. We take that and we square it, multiplied by p hat times q hat. We divide that all by the margin of error squared to find our sample size required to estimate a population proportion. Now, when we don't have an estimate of p hat, we use a slightly simplified version of this formula, but it still is very similar. So our z subscript alpha over 2, our critical value squared. Then because we don't know p hat and we don't know q hat, then we multiply this by 0.25. Then we take this all again divided by the margin of error squared, or E squared. Now we're still talking about how to find the sample size required to estimate a population proportion. So there is a round off rule here, and it's a little bit different than what you've seen before. So if the computed sample size n is not a whole number, then we round the value of n up to the next larger whole number. We do this because we'd rather err on the side of caution, so the sample size should be sufficient rather than being just slightly insufficient. So we want to take that non-whole number value, round it up to the next whole number. An example of doing this, let's say we went through that equation, we got 1067.11. We're going to round this up to the next whole number of 1068. So the key here for sample size, do not round down, always round up to the nearest whole number. If we get a whole number as is after doing that calculation, then we leave it as that whole number. Let's do some examples of using those formulas. So an example, what percentage of adults have made online purchases or make online purchases? Let's say we're really interested in collecting this data, so we're going to make a survey, and we want to know how many adults must be surveyed in order to be 95% confident that the sample percentage is in error by no more than 3 percentage points. Given this background information, then we can assume that a recent poll showed 80% of adults make online purchases. Then in B, assume that we have no prior information suggesting a possible value of the population proportion. So you may start to recognize now that we'd use the first formula for question A and the second formula for question B. So let's try this. In solving for both A and B, let's first figure out what we know. So if we have a 95% confidence level, that corresponds to a critical value, or Z subscript alpha over 2, of 1.96. We've solved this a couple times, but make sure you are comfortable going from a confidence level to a Z subscript alpha over 2 for a critical value. We know from that table in part 1 that this 95% confidence level corresponds to a critical value of 1.96. Let's define success and failure now. So we can say the measure of success is that an adult makes online purchases. From part A, we know this p-hat value is estimated to be 80% of adults do make online purchases. Taking this p-hat value out of a percentage, that's 0.8. This bullet point here corresponds only to what we know from part A. Next, if we know our p-hat value, we also need to define a measure of failure now. So that can be adult does not make online purchases. In order to solve for q-hat, then we take 1 minus 0.8, we get a q-hat value of 0.20. This bullet point as well only pertains to part A of the question. This next bullet point here pertains to both parts A and B. It was given in the main part of the question, so no more than 3 percentage points in error. How do we interpret this? Well, 3 percentage points in error, that's our margin of error value. That's our E value. So again, we take this out of a percentage by going from 3% divided by 100. That's equal to 0.03. So again, when reading that out, no more than 3 percentage points in error, think of that as our margin of error value, as our E value. To visualize what this means again, we can have our point estimate here. We have our confidence interval limit. That's our p-hat value, or our point estimate, minus some margin of error, and then plus some margin of error. So we're really getting 3 percentage points on this side of the point estimate, and we're allowing for 3 percentage points on this side of the point estimate because this question says no more than 3 percentage points in error. That means we can go below the point estimate by 3 percentage in error points and above this estimate in 3 percentage error points. And remember, E, our margin of error, that refers to this half and this half. So this is 3% and this is 3%. In a non-percentage, this is 0.03 and this is 0.03. In this style of questions we're on now, we're trying to solve for the sample size. So in this case, n is unknown. So again, this bullet point pertains to A and B, as does this one, and as does this one. So now let's solve for A separately and B separately. Again, the question for part A, assume that a recent poll showed that 80% of adults make online purchases. We know from the last slide, we take this 80%, that's considered our p-hat value. So 0.8 is our p-hat value. Then we ask ourselves, which equation do we use? Do we know an estimate of p-hat? Well, for part A, yes, we do know an estimate of p-hat. That means we use this version of the formula. So let's plug in what we know. Let's solve for sample size. So again, we need to take our critical value, square it, multiplied by p-hat, multiplied by q-hat, all divided by our margin of error, or E squared. Plugging in numbers here, this is 1.96 squared multiplied by 0.8 multiplied by 0.2. Then we divide this all by 0.03 squared. Notice in all of these numbers, we don't use the percentage form of the values. We use the decimal forms. You can use Excel or use your calculator. We can solve for this. We get a larger number here. That value is 682.951. That is not a whole number, so we need to round that up. It doesn't matter what comes after this. If it's not a whole number, we always round up. So our final answer here is 683. Another way to say this is that we must obtain a simple random sample that includes at least 683 adults to then satisfy the requirements of this question. Let's solve for sample size in question B now. So to remind you of that, assume that we have no prior information suggesting a possible value of the population proportion. For this style of questions, again, we ask, do we know an estimate of p hat? Here for part B, the answer is no, we don't have an estimate for p hat. Because we don't know p hat, we can't figure out q hat either, so we need to use this form of the formula. So again, in other words, we have, quote, no prior knowledge other than our margin of error value, or E, and other than the 95% confidence interval, because from that is where we got our Z subscript alpha, or our critical value. We also weren't given anything else in the question that would allow us to solve for P or solve for Q. So here's our formula again. Then we plug in the values that we know. Because we don't have a P hat or a Q hat, we just use this term here of 0.25. When we use Excel or use our calculator, we get 1067.11. Again, for all these sample size questions, it doesn't matter what this value is. If this is not a whole number, we would normally round down. But here for sample size estimates, we always round up. So it doesn't matter if this is 0.11. We take this value, we round it up to 1068. Another way to say this, we must obtain a simple random sample that includes at least 1068 adults. Now let's more specifically talk about this interpretation and make some connections when we have an estimate of p hat and when we don't. So here, to be 95% confident that our sample percentage is within 3 percentage points of the true percentage of all adults, we should obtain a simple random sample of 1068 adults. Remember, we got this value using part B. This was assuming no prior knowledge. However, in part A, when we did know p hat, then comparing the two results, in part A, we got 683. 683 is definitely less than 1068. So let's make this connection now. So we can see that if we have no prior knowledge of a prior study that was done, then a larger sample size is required to achieve the same results as when the value of p hat can be estimated. In other words, if we know p hat, then our sample size requirements are smaller than if we don't know p hat, if we don't have any prior knowledge. Okay, here in 7.1, all those formulas are important to know. Always check the requirements. Can we use those certain formulas? I recommend, again, drawing diagrams, drawing pictures. And in addition to computing and using the formulas, make sure you check, do we understand the interpretation of those values? This is the end of 7.1 now. I hope you're all doing well. Let me know if you have any questions, and I'll see you next time for 7.2.